So moving on. So I want to talk about a really cool modern technique in spectroscopy, which you likely haven't talked about in any of your classes. And this is taking advantage of doing single beam spectroscopy. So we call this difference or sometimes action spectroscopy. And so the idea here is this is still very much a single beam instrument, okay, except for our our background single beam spectra and sample single beam spectra are truly identical. So meaning that we would have analyte molecules here as well as analyte molecules here. And now in between these two samples, so in between the time that I record the initial background single beam and sample single beam, I've done some chemistry. Okay? And so if anything happens to that sample in between these two conditions, then the absorption spectra will only reflect the changes that happened. So that's why we call this difference spectroscopy, right? And one really good way to note what you kind of expect out of these spectra, all right? So if, let's say, nothing happens, literally we don't do a single thing from the background to sample. So we just leave it in there, we record a single beam, we don't do anything, we record another single beam, and we take the negative log ratio of those two single beams, right? So just, I'll remind you, right, to do an absorbance, we would take the negative log ratio of condition 2 over condition 1, the single beam spectra. So if nothing happens between, then we'll just get a blank line. And I'm going to draw it with kind of like some noise, right? Because it won't be like a perfectly blank line. You know, there'll be some noise. And I'll say that that blank line will occur exactly at 0 absorbance. Because the negative log of 1 equals 0, right? So if these two spectra are identical, then ratioing them won't reveal any changes took place, okay? And so we'll say this is absorbance, and we'll say this is wavelength, all right? So now let's suppose that something happens, that we do some chemistry in situ with the spectrometer, right? So that could be accomplished by some convoluted apparatus that allows us to flow reactant molecules into that cuvette, or it even could be something as simply as just spiking our sample with something in between these two conditions, right? If that doesn't give an appreciable volume change, right? Suppose we just spike, you know, like 1 microliter of a reactant, that won't have changed the volume all that much. And so we'll see some chemistry happen. So now our absorbance spectra will no longer be a blank line. Rather, we will get positive features if some new, let's say, functional group appears as a result of the chemistry. All right. And also, we will see negative features indicating that there's been a loss of some functional group, or even if this were UV vis, right, we don't see functional groups in UV vis, but rather we would just see a peak associated with the chemical bond that was lost and a peak associated with the chemical bond that was gained. And so in this case, you know, a positive absorbance and a negative absorbance are very significant. They mean that something has been gained or something has been lost. So I want to share some results with you from one of the first papers that did this, 2007. This is from the Finlayson and Pitts group. They're an atmospheric chemistry group at UC Irvine, where I went to graduate school. So the Finlayson and Pitts group is world renowned at being atmospheric chemistry spectroscopists. So Dr. Finlayson and Pitts more or less perfected this technique. So it was very cool to get to learn it from her. So this is a fantastic example. So this is an IR spectrum, so it's Fourier transform. But what's important to note, it's a fantastic demonstration of this difference spectroscopy. Okay, so in this reaction, there's some sodium sulfite, and sodium sulfite is oxidized by ozone and other oxidizing agents of the like to make sodium sulfate, okay, plus some oxygen to be stoichiometrically correct. All right, and so the way this experiment goes, you've got sodium sulfite as your sample, and you record a single beam spectrum of that. And to get this sulfite peak, this also had to be ratioed to a blank sample. So this is like a ratio of a ratio of ratios, okay? So otherwise, if it had only been condition 1, condition 2, this would be a blank line, okay? So you can get a little bit more sophisticated than just 2 conditions. You can add a third condition to get yourself the initial starting peak, right? So now what happens is ozone is pumped into the sample chamber, okay? And I'll show you some technical aspects of this later on in the week's talks of how you can achieve this. But in any event, gas phase ozone is flowed over the surface of this sample, which initiates the reaction, and successive single beam spectra are recorded in time. And you can see in this example, one at 5 minutes and one at 15 minutes. And what's really cool, as you can see, after 5 minutes, which is this gray one, I'll get a different color so we can see it. The sulfite peak has reduced, okay? And by reduced, I mean its intensity is going down, okay? And also you can see here, this region is where the sulfate peak would be, and its intensity is going up. And under further reaction, now the sulfite peak has more or less completely been titrated away, so it's gone. And now it's been replaced with sulfate. So this is a really, really cool way to prove a mechanism because you're seeing simultaneously the destruction of functional groups and the creation of new functional groups. And so this is a different paper here, same group, but different system. And actually this goes back to 2002, so this wasn't quite the original. But for several decades, they spent, several years, I should say, they spent perfecting this technique. Okay. And so this is a fantastic demonstration that actually shows a true action spectra where the T equals 0 spectra is just a blank line. You can kind of see it right there, right? And then it gets noisy as you get into the smaller wave numbers. But now you can truly see here the loss of some functional groups, right? And the gain of other functional groups, which again is so cool for your chemistry and your kinetics and doing your mechanisms. Really, really cool technique. And I'll plug my own lab. We have the ability to do this technique in my own research lab. So I'll spend some more time talking about that later on in the week. Okay, and so that's a good place to stop because where I'm going next is getting into pure rotational spectroscopy. After that, we'll talk about pure vibrational spectroscopy. After that, we'll see how the rotations and the vibrations actually sync together to do row vibrational spectroscopy, so simultaneous rotational vibrational spectroscopy. And then at the end of the semester, the last few weeks, we'll get into the electronic spectroscopy. Okay, folks, I'll see you in the next video.